So here you can see that we have the alkali metals, which is group 1 of the periodic table. So we go lithium, sodium, potassium. What I would like for you guys to see is that as you move down the periodic table, notice how the shells increase. So lithium is in the second period of the periodic table and has 2 shells. Sodium is in the third and has 3 shells. Potassium is in the fourth period of the periodic table and has 4 shells. And then cesium is actually in the 6th period, and so it has 6 shells. So as you go down the periodic table, the size of these atoms keeps getting bigger and bigger and bigger. The other thing I would like for you guys to notice is that each of these, if you look at the very, very, very last shell, so if you look at the second shell in lithium, the third shell in sodium, and the 4th shell in potassium, all of these have 1 valence electron. So they have 1 electron in their outermost energy level. That 1 electron makes them extremely unstable. So just how unstable are they? Let's take a look.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal's surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a light flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
So again, as we went down the periodic table, as we went down the group, they became more reactive. The reason why they became more reactive is because you can see that this valence electron, this 1 valence electron in their outermost energy level, gets further away from the nucleus, and therefore it leaves very, very quickly. So cesium exploded when it was placed in water. Now, these as they appear are completely unstable. But if you want to make them stable, then you would lose that 1 valence electron. If you lose electron, then you have an ion. An ion is any atom with a charge. What that means is that the protons and the electrons are not equal. If you have more protons, so if you lose electrons, then you're going to become a cation and you're going to have a positive charge. If you add electrons, then you're going to be an anion and you're going to have a negative charge. So take our buddy fluorine, for example. Fluorine has 7 electrons in its outermost energy level. It is really unstable as well. But it doesn't want to lose 7. That would be too difficult. So instead, fluorine is going to add an electron. So if it adds 1 electron, then its charge will be negative. Now, just like there's a pattern for valence electrons on the periodic table, those valence electrons will correspond to our ion charges. So here in the very first column, so just like we have a pattern for valence electrons, those valence electrons are also going to tell us what charge the anion or the ions are going to take. So we know that there is one valence electron in the first group. It is much easier to lose that one valence electron to become stable. So when it loses that one valence electron, it's going to have a charge of +1. In the second group of the periodic table, these have two valence electrons. In order to become stable, they want to lose both of those valence electrons. So they're going to take a charge of +2. The boron family has 3 valence electrons, and so it's going to want to take a charge of +3. Carbon group is a little strange because the carbon group actually has 4 valence electrons, and it's just as easy to lose the 4 as it is to gain the 4. So we're going to say that it could be plus or minus 4 because it could lose the 4 or it could gain the 4. These tend to bond in a different way besides ionic bonding. The nitrogen group has 5. In order to achieve some stable configurations, it's actually easier to add 3 electrons. But when we add 3 electrons, now we have 3 more negatives than we do positives. So therefore, everything in this group is going to have a -3 charge. Oxygen is going to have a -2 charge because it wants to gain 2 electrons. Fluorine, like we looked at earlier, is going to have, and everything in fluorine's family is going to have a charge of -1. Now, the noble gases already have 8 valence electrons, except for helium that only has 2. Everything is already full. So because these are already full, they're what we call inert. They are not going to react to anything. And so the charges also correspond to how far away you are from your noble gas configuration. Fluorine is only 1 step away. Oxygen is 2 steps away. Nitrogen is 3 steps away. If we look at sodium, we have to lose 1 electron to get back to our noble gas, which would be neon. So again, the charges could also correspond to how close are you to your nearest noble gas.